Hello and welcome to week 8. I can't believe this semester is going by so fast. I'm about halfway through grading your research proposals. I went out to lunch with a couple of CS professors a couple days ago, and they showed me a way to download all of your submissions, making my life about a million times easier. So that should get done relatively quickly. There is another video on regression, which I'll slightly touch upon on this video. Today I want to cover machine learning, just real big basics of machine learning. I hope that your path so far through UNLV has allowed you to at least learn some type of machine learning and some major concepts of machine learning. And that's all I'm just going to really kind of go over today as a recap of machine learning. Machine learning, as it is today, 2023, in my opinion, has come from two major changes in industry. So let's say from 20 to 15, 10 years ago, all the companies were trying to sell this big data. Hey, get big data. Big data is going to change the world. Big data this, big data that. You see ads for, hey, our database can handle big data, or our whatever, our C plus or Visual Basic Processor can handle big data. So big data was really a heavy, I won't say marketing term, but it was a heavy marketing term from maybe 20 years ago to 10 years ago. So everyone used to grab this big data marketing. Well, from there, we had all this data, but we really didn't know what to do with it. We really couldn't process it. The cloud wasn't really a big thing, and individual machines couldn't process it. And the data you really want to upload to a mainframe, so it was just kind of sat there. It was kind of this ether of unknown. So about maybe 10 years ago, 8 years ago, something like that, people started using GPUs. Richard, what's a GPU? A GPU is a graphical processing unit. So, you want to play Doom or World of Warcraft or any game, you have a video card. Those video cards are use specialized functions, specialized features, particularly matrix math, matrix algebra, not matrix algebra, matrix math, and that can be applied to processing a lot of data at any one time, and that really revolutionized how machine learning could actually process through large chunks of data. One of my machines behind me has the newest Radeon chip on it. It's 7950, 7950X, whatever it is. So it has 32 cores. If we think about that, that means that it at any one time can process, which is not really true, but it can process 32 chunks of data at a time. So 32 variables, maybe 32 variables, 32 variables. That's pretty amazing, and it can do it, I don't know, a lot. However, once you start to think of things at scale, that's not really that significant. Because my GPU can do, 3,000 cores, 4,000 cores. So it's just inherently that much faster. So why don't we have GPUs instead of CPUs? Well, GPUs provide very, very specific instructions, very, very simple instructions, okay? Very, very basic instructions. So they can't handle opening Word and doing these generalized instructions. Okay, and I guess some ways to think about it is that me as maybe like a homeowner or an apartment owner or apartment renter, I can do certain handyman work. Maybe like I don't change the thing under the sink, the U trap or whatever it is. Now, if I was to do that, it would take me maybe 3 hours. If I was to call a plumber, say, hey, can you do this? Since it's specialized and that's all he does, he probably can do it in 15 minutes. I can probably wire a room for network or electrical stuff. Again, it might take me 3 or 4 hours to do it. I could call an electrician. He could do it in half an hour. He specializes in that. The problem is when we ask an electrician to do the thing under the sink, the U-trap under the sink, it might take him even longer than me. Because he has to come out and I surprise, hey, can you work on my sink? And he's like, no, I don't have any of the tools. I'm like, you have to do it. Well, he'd have to go to the store, buy the tools. He'd have to go and get training on how to. It would take him even longer than me to do that. So that's the difference between just a general CPU, central processing unit, and a GPU, an NVIDIA GPU or AMD GPU. Now, continuing down that road, a lot of things I do, like scikit-learn, I just use on the GPU because it's a small data set, and inherently it's fast. Now, if you're talking video, big data sets, most of the time we move those over to a GPU or TPU. In the GPU world, and I'm not endorsing any particular brand or anything, but right now, currently, NVIDIA is more or less the king of everything. They've had a stronghold on GPUs and machine learning processing for a while now. AMD is developing OpenGL, and it works really well. Apple's coming out with Metal and other technologies, and they, both of them work well. They just don't have a stronghold. If you write a program using NVIDIA library and things like that, CUDA, you can't really port it over all the time to OpenGL very easily. So that's where the problem is. So that's kind of how we got to where machine learning is so popular today. Big data, 10 to 20 years ago, and then 10 to 5 years ago, GPUs really came on the scene and just could rip through data like nobody's business. So today, I just want to go over the real big ideas: supervised learning, unsupervised learning, and reinforcement learnings. And that's kind of what I talk about: big data to big answers, which actually led to more questions. So don't think that supervised learning is better than unsupervised learning, and that deep neural networks are better than supervised learning. It doesn't work that way. You can't compare a plumber to an electrician. They're different tasks, they're different jobs, they have different skill sets. Okay, a plumber is better at plumbing, and an electrician is better at doing electrical work. Supervised learning is better for doing tasks that it's suited to do: regression, classification. Unsupervised learning is better at clustering. Reinforcement learning might be better at time series data, neural networks. So they're all different, and they all have their role in it. Also, another thing to remember is that machine learning is not a new concept. It may be a popular concept, but it's not new. Machine learning goes back 80 some years. Okay? So, before we get into this, let's think about, and I have 3 examples here of how using business intelligence, that's the core of this class, is business intelligence, how machine learning can help us. Because I don't want to get into the math and the nitty-gritty of machine learning. I want you to understand, as a tool, how can machine learning help you get to the goal of producing intelligence that can change an organizational culture or lead a leader to make more intelligent decisions. First, deep learning can analyze large amounts of complex data to uncover insights that would be difficult for humans to find. So you have to realize too that humans are just pattern detection machines. As you guys know, I'm a neuroscientist. That's what I do. I do neuroscience. Neuroscience is the study of the brain. Now I can tell you that humans are phenomenal machines at discovering patterns. We discover patterns when there's not even really patterns there. And patterns is a lot of the reason for cognitive bias and many other things that I've tried to help you understand. The problem is, if we're looking at a large set of numbers, just a large Excel spreadsheet, large CSV of millions of rows, we might not be able to derive patterns that aren't very, very apparent. Okay? And we'll go into a quick little example during this. Well, we won't go into an example, but I'll show you a regression what I'm talking about. Second, deep learning can be used to make accurate forecasts and predictions about the future business trends based on historical data. Now, time season. So, we look at time season data, and there is an old story about polio and ice cream. And it just shows that as humans, we don't always have time series information readily available. While we can see patterns, we can't always see time series patterns. Okay? So time series patterns are things that may happen seasonally, every quarter. It may happen every week. It may happen every microsecond. It may happen every 3.5 hours. Machine learning is inherently good at predicting seasonal or trends based on time season data. It doesn't have to be, what me and you think of as a calendar time season. When I say time season, it can just be a variable of time. It can be microseconds. It can be years. It can be centuries. It can be days. Third, deep learning algorithms can automatically cluster and segment customers, helping drive personalization marketing efforts. And deep learning can see things that we might overlook or we might not think about. So let's talk a little bit about traditional programming. As I stated a while ago, I went to lunch with some CS guys. And I'm no programmer by a long shot. I'm a data guy. I'm a scientist. I'm a strategic analyst, much more so than a programmer. But I have taken programming classes, and one of the things in one of the very first programming classes that we talked about is how would you write, just in human English, how would you write a program to open a door handle, or open a door, I should say. And it is rather complex. What if it's a lever door versus a knob? What if the door pulls in versus pulls out? What if you're sitting down versus standing up? There's hundreds of different scenarios that if you write a program to open a door and basically go through the door, you can have hundreds of rules. A, stand up. B, approach the door. C, stop at the door. D, find the location of the knob. E, analyze the type of the knob. Does it go up and down? Is the door locked? Is there a deadbolt? So when we think of a program, and as a programmer, we have to think of a list of rules. So we give it input. Think of a ton of rules, debug those rules, think of more rules when those rules don't work, and then continue debugging and keep going until we have something that works most of the time. Machine learning is a very different type of programming. We don't necessarily worry about the rules. We want to give the machine A an input and B a goal and say, hey, go from here to here. Go from here to here. Just learn how to do it. And we do this by neurons, backpropagation, but a bunch of different methods. So here's the data. Here's where I want you to get. Just keep doing it until you basically fail until you succeed. And if you think about how does a child learn how to walk? We don't give them a lot of rules. We pick him up, he walks, he falls. We pick him up, he walks, he falls. He backpropagates his brain. He forward feeds his brain. Okay? He walks a couple steps and falls. Walks a couple more steps and falls. Maybe walks more steps, leans on a wall, walks more steps and falls. He continually revises his input and output. He comes up with the rules in his brain. He knows that if he walks and leans forward too much, maybe he falls. If he leans back too far, he falls. So he does it basically almost not necessarily by a rule-based hierarchy, but by trial and error. And that's kind of how machine learning is. The problem with that, as we talk about in ethics, is that when we allow machine learning, I don't want to say I don't know why, when we allow machine learning to process data in a production environment, we have a black box. We don't know how machine learning got to that answer that it did. We know that we fed it X data, we know that we got Y output. But how, we don't know. If I was to ask you, how do you regulate your thyroid gland? You couldn't tell me. You couldn't write a mathematical formula or a list of rules on how you regulate your thyroid gland, how you see the sky as blue, how you open a door every time without fail. But yet you still do. It's that black box effect that many people worry about in terms of machine learning. Because we don't know what's under that or inside that thinking part of machine learning. The neuronal weights. Now they're working on it. And a lot of the more modern or at least research-based machine learning, it supports decision support. So the machine says, hey, I recommend this because of that. while it's still a few years out, it is becoming more and more popular. So the first one we're going to talk about, just real big picture, is supervised learning. This is the next video is also on supervised learning. Yeah, for some reason it was cutting off the bottom of the screen. Okay, so again, don't think supervised learning is better than unsupervised learning. It doesn't work that way. But basically, the 10,000-foot overview of supervised learning is simple. Predict new outputs for unseen inputs. Think about it. Our goal is to predict new outputs for unseen inputs. That's why we go to college. We know that, hey, if we go through college, we'll get more money. We'll be more educated. I have a really simple data set. Let me pull it up. Okay, this is just something I found on the internet real quick. And when we go to the demo, we'll do a little bit heavier demo on this. But the years of experience that you might have as whatever, teacher, a data scientist, whatever job, right here. And salary. And you see, hey, as one goes up, the other one goes up. Most of the time. This one went down, but most of the time it goes up. 2 years, you get about, I don't know, if I average those two, about 40 grand, 30 or 41 grand. If you have 6 years, you get 80 grand. So that goes up. So it goes up kind of, with more years of experience. But the problem is, let's say I have an employee that has 12.5 years, or 12.65, or 15 years, or 18.8 years. What's the salary? I know you can't see that because my screen cut it off. There we go. What would his salary be? Or her salary? We have to predict, let me go back here. We have to predict outputs. What is her salary from unseen inputs? Well, we don't see anybody here. I mean, I could say, hey, what do you expect somebody with 5 years experience? Well, Richard, I expect them to be between 66 and 67K. I mean, that's no big deal. But we don't have, sorry, excuse me, anybody that has 12 years of experience. We don't have anybody that has 15 years of experience. So how do we, these are unseen events. So how do we make a prediction? Okay, so that's linear regression. We also use supervised learning for classification. Unsupervised learning, unsupervised learning is a clustering, a way we can group data points together. It's also a lot, or very commonly, dimensional reduction. Now, with dimensional reduction, it's basically taking a bunch of columns, which is a horrible way to explain it, but taking a bunch of columns and reducing them to what's important. There's a bunch of different reasons we do this. One is we avoid, it's called the curse of dimensionality. But basically, sometimes we have just so much data, it doesn't always help solve the problem. We do this for computational efficiency because we don't want to be able to process 10 million rows. We do this for noise reduction sometimes. Also, another reason we do unsupervised learning is if I have a data set that has, 20 or 30 dimensions, I can't plot it. If I have some type of machine learning method, or if I have something that I design and it has 14 dimensions, I can't plot that to show somebody. So I have to reduce it. I have to reduce the dimensionality of it to 2 dimensions or 3 dimensions. In the regression video, I'm going to talk about multicollinearity. Such a hard word for me to say. Dimensional reduction can help deal with this. There's a couple different types of dimensional reduction. For example, there's PCA, which is really common in data science. There's also T-sign, which I tend to use a little bit more. There's LDA. So that's one of the main reasons I use unsupervised learning. That and, like I said, clustering. And what I mean by clustering, you have a lot of data points. Let's see, iPad. There we go. So you have lots of dots, and you want to figure out, hey, this one and maybe this one are the closest together. And it could be age. You have a bunch of just the number of ages, 15, 16, 15. You might have a 30, 31, 15. So you might have a bunch of 38. You might have 60, 15, 30, 72, 18, 32, 71. So if you look at these, it's pretty easy to spot the pattern right now. You have, I don't know, teenagers, people in a midlife crisis, and then seniors, okay? So, I mean, and it's like this would go up here. Let's see, this one would go up here. This one would go here. So you can kind of see how you would organize that just in your head. But it's not always that obvious. And it's always not always that easy. Okay? The objective is to uncover insights from data sets without guidance. And finally, you have, there we go, oops, reinforcement learning. Reinforcement learning is when we use neurons or different methods to try to do that trial and error. As a baby is learning how to walk, I got up and I fell down. Well, I know if I get up and lean forward a little bit, I put my foot in front of me. It's a trial and error. And I have a little video that we're going to watch that will help explain this a little bit. So it's a great video. And again, it talks about common examples, but reinforcement learning is basically the catch-all in many ways. There's a lot of other ones in between. There's semi-supervised learning. There's one-shot learning. There's zero-shot encoding. There's a bunch of different ones in between. In my mind, these are three big ones. Like I said, there's a bunch of subtypes, but you have supervised, unsupervised, and reinforcement. Like I said, you got some oddballs out there, semi-supervised and one-shot. These are the big ones. So, really, in order to understand, again, maybe this is one of my pet peeves because I study neuroscience, which studies neurons. We have to really kind of understand the biological neurons, which the artificial neurons was derived from. And the problem is when we kind of look at the biological neurons, we don't really get the full gist of it. We don't understand all the intricacies of it. Let me move this over to my iPad 1 second. Okay, somewhere right about here is where we were. So we look at these biological neurons. And basically what we have is input over here and output over here. Okay. But now, a couple things are missing big picture here. One is that is this output to another neuron or to a muscle? And it can be either way. Okay. This often attaches to another neuron, so I'll just put like this and put an N in it. And that connects to another neuron. Okay. Now there are some neurons in the body, many of them, that connect to a muscle. So what happens is when that neuron fires, you're going to get a movement. Okay? And this is so important to understand because basically that is what a lot of these graphs don't always, or a lot of people don't always understand when we look at this artificial neuron. Okay? That at the end of the day, there is an activation layer or some type of function that says, yes, this is a 3, or it's a binary output, true or false, or some other end of the day activation. It does something. Okay. Now, another thing too, do both of these here. Remember, with neurons, both in biology and in artificial neurons, if we get 3, and this might be true, this might not be true, but it's true, it's just how we think about it. If we get 3 small or 4 or 5 small firings, small firings, they might sum up in here and actually create an action potential. Same thing here. You might get a really small one. And if you get a bunch of these small ones, it might lead, they might sum up to an activation. They might do something. Okay? Or you might get no on a lot of these little ones, and then one really big one. 0, 0.1, 0.1, 0.0, 0.01, 0.999. So sometimes it is a big single input that creates a firing. Okay? And two, remember with biological neurons, more or less, 'cause it's not always the case, and just as it is with machine learning neurons or artificial neurons, is that it's an all or none system. It either basically never fires or it fires. It does one or the other. It doesn't fire or it fires. So to get to that action potential, you have to reach a certain threshold. Okay? If you don't reach that threshold, nothing happens. And what do I mean by that? So we have second 1, we have second 2, we have second 3, we have second 4, second 5. Second 1, we have point 1, point 1, point 1, point 1. Nothing happens. Okay, so our neuron resets. Second 1's gone. Second 2, we have point 1, point 2, point 1, point 0, point 3. Still, nothing happens. Same thing, nothing happens over here. So we can get rid of, I should just cross these out. Well, then we have point 1, point 1, point 9, point 1, point 0. Now we have a big spike and we get something that flows through here. So second 3 causes a fire, an action potential. And that either gets passed on to another neuron, and this neuron might or might not fire. Why? This neuron might not fire even though the neuron before it did, because this one might not have enough input to create another action potential. It might not have enough to activate the next layer. And you see that down here. That's why this is kind of such an important idea. If this one fires, does this one fire? Maybe, maybe not. And if this one fires, does this one fire? So we know that, hey, maybe it takes all 3 of these targeting this one neuron to make this one fire. And then when this one fires, it fires on these 2 right here. But then it dies, it doesn't go anywhere else. We never get an output. We never get a motion. A mosquito lands on your arm, you don't realize it. There's not enough inputs to cause a reaction. You're walking down the street, you step on a nail, and these are all 0.9, 0.9, 0.9, 0.9. And boy, every neuron fires because you just stepped on a rusty nail, and you're screaming in pain. So everything fires. So like I said, and there could be thousands of hidden layers, and it could be one hidden layer. Okay? Here's a little more detailed look at that. And another thing to remember too, and I hate to say this, is that these are super oversimplified systems, iPad. So when we look at dendrites, they can have thousands of inputs. They have 10 inputs. They have a million inputs. They can have a branch off here to another neuron. Another neuron. We have another neuron up here. This thing can branch off and grab 10 different inputs to do summarization to it. These are very, very oversimplified things. Same thing, as with artificial neurons. They tend to oversimplify things. Oh, my video. Let's see if I can pause it here. Pause. Okay, so I'll post a link to this video. I fast forward through some of the stuff in the front of it, but this is a really, really great video. It goes over the basics of what I just covered with neurons. So let's see if we can watch it, and I think this is the last. Actually, I think there's one other slide after this. So let's watch this real quick. It's like 4 or 5 minutes, and we'll go over this and a few other things.
Let's understand how this is done. Let's construct a neural network that differentiates between a square, circle, and triangle. Neural networks are made up of layers of neurons. These neurons are the core processing units of the network. First, we have the input layer, which receives the input. The output layer predicts our final output. In between exist the hidden layers which perform most of the computations required by our network. Here's an image of a circle. This image is composed of 28 by 28 pixels, which make up for 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons of one layer are connected to neurons of the next layer through channels. Each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is then passed through a threshold function called the activation function. The result of the activation function determines if the particular neuron will get activated or not. An activated neuron transmits data to the neurons of the next layer over the channels. In this manner, the data is propagated through the network. This is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. The values are basically a probability. For example, here, our neuron associated with square has the highest probability. Hence, that's the output predicted by the neural network. Of course, just by a look at it, we know our neural network has made a wrong prediction. But how does the network figure this out? Note that our network is yet to be trained. During this training process, along with the input, our network also has the output fed to it. The predicted output is compared against the actual output to realize the error in prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. The arrows here give an indication of the direction and magnitude of change to reduce the error. This information is then transferred backward through our network. This is known as backpropagation. Now, based on this information, the weights are adjusted. This cycle of forward propagation and backpropagation is iteratively performed with multiple inputs. This process continues until our weights are assigned such that the network can predict the shapes correctly in most of the cases. This brings our training process to an end. You might wonder how long this training process takes. Honestly, neural networks may take hours or even months to train. But time is a reasonable trade-off when compared to its scope. Let us look at some of the prime applications of neural networks. Facial recognition. Cameras on smartphones these days can estimate the age of the person based on their facial features. This is neural networks at play. First, differentiating the face from the background, and then correlating the lines and spots on your face to a possible age. Forecasting. Neural networks are trained to understand the patterns and detect the possibility of rainfall or a rise in stock prices with high accuracy. Music composition. Neural networks can even learn patterns in music and train itself enough to compose a fresh tune. So, here's a question for you. Which of the following statements does not hold true? A. Activation functions are threshold functions. B. Error is calculated at each layer of the neural network. C. Both forward and back propagation take place during the training process of a neural network. D. most of the data processing is carried out in the hidden layers. Leave your answers in the comments section below. 3 of you stand a chance to win Amazon vouchers, so don't miss it. With deep learning and neural networks, we are still taking baby steps. The growth in this field has been foreseen by the big names. Companies such as Google, Amazon, and Nvidia have invested in developing products such as libraries, predictive models, and intuitive GPUs that support the implementation of neural networks. The question dividing the visionaries is on the reach of neural networks. To what extent can we replicate the human brain? We'd have to wait a few more years to give a definite answer. But if you enjoyed this video, it would only take a few seconds to like and share it. Also, if you haven't yet, do subscribe.